Well, I guess we can all go to our work tomorrow and say that we're really good at Monopoly. So let's hope the same applies to name matching. First of all, as you can see, the presenters, Wendell Kuling, that's me. And Chris Broer unfortunately couldn't make it today, but he contributed largely to this presentation, as did Alex, who's sitting in the back there, who did a large part of the GPU computing things. We're working at the ING Wholesale Banking division as data scientists. And as the presentation, we would like first to explore the problem together with you, then discuss 3 approaches to solving this, and then show you some practical implementations of how we actually did it. So the wholesale bank, that's the part of the bank of ING that deals with corporate clients or other financial institutions. So not the retail part, but really the bank for large companies. And of course, we like to combine different data sets of companies. And often we encounter the situation, as I'm pretty sure all of you do, that the key on which we want to match this data is somewhat close to each other, but not exactly the same. So for example, one company, McDonald's, that might be called McDonald's without any punctuation marks in one data set, and McDonald's with an accent in another one, and Corp behind it in yet another one. So lots of different opportunities to spell McDonald's. So what we really need is a way to match approximately to tie these data sources together. Some definitions. We have some ground truth table. We call that G. Coincides with the name we use for that internally. And we have some sources we would like to match to that. So we call them S1 to S2, S3, but without loss of generality, let's refer to those as G and S. G is the ground truth table, S is the source we can get in. So there are many ways to look at this problem. You can think about it as an approximate string matching problem. You can think of it as a pattern mining or pattern recognition problem, nearest neighbor search problem. Anyway, again, the key is finding the closest name in G for every single name in S. So that's the challenge we're up to. I'm pretty sure you're up to many times as well. So to give you a little bit of a feel for the numbers, G in our case has 12 million entries, and S ranges in length depending on what we get in. We might get in a list of a trader which has noted down some names in Excel with some comments which we would like to attach to this ground truth, and then it's 3,000 list long in Excel, and it might be 5 million names relating to some other payments database we would like to link to the ground truth table. On average, a name is 31 characters long. That includes the name of the city, containing 4 words. We have, I counted them this morning, over 160 different characters being used. That's due to the geographical presence of ING. We also have a lot of exotic characters as a result thereof in the names of the companies we serve. And there are limited duplicates in G, but some companies are quite close to each other in terms of name. So, how to solve this problem? Well, brute force is of course a first candidate. I think you did the same, right, at Monopoly. So let's try brute force for name matching as well. We just define a function which measures closeness. Closer the names are, the higher the score, and the higher the similarity is. Just compare each word against G and see whoever is closest. We match them together. You can choose different closeness measures and then ensemble the results to make the results better. Many word similarity functions. Levenshtein is a very common one, counting the number of edits you need to go from one string to the other. What counts as a point or a score, if you will, is a replace, addition or subtraction. In Dammerau-Levenshtein you also have swaps. So if we transform or compare ABN AMRO Bank to Royal Bank of Scotland or RBS Bank, typically there will be two replacements, right? The A needs to be replaced by an R, and the N needs to be replaced by an S. If you leave out AMRO, those two banks are exactly the same. So that's a distance of 6 in Levenshtein terminology. And then the brute force method would be for every entry in G or for every entry in S, if you will. It doesn't really matter because you're going to do them all anyway. You calculate this distance metric, this distance function I should say now. It's also a metric by the way. And compare them, for example, for the first entry, second, and so on. So with 12 million names in G, this turns out to be not the best strategy thinkable. You might have as well have guessed by the fact that it's first in my presentation, but it requires us 60 trillion similarity calculations, and although we have a powerful cluster at ING, this is actually asking a bit too much of it. If you would be able to do 10 similarity calculations second on a single CPU, I should say, you would still be left with a task of 190,000 years of calculations. Suppose we would have 10,000 cores at our disposal, still it would be 19 years. That wouldn't be a good solution. If you have smaller sets at your disposal, these are good packages to consider. So if you implement it in pure Python, it can be reduced to a factor of, I think it's around 10 to 20 or so if you use a smarter package. PyData is a really good one with a highly optimized C code. It's the fastest. Jellyfish is a good second. Fuzzy Wuzzy, that's a nice package which does a lot of this brute force method already in a quite nicely callable API for you. But again, do notice that it is not that scalable. So if you have 1 million entries on your ground truth, trying to match one element to that will take around 120 seconds on a single core. So metric tree approaches. If we choose the right distance function, which obeys these properties, you might be familiar with them, but if the distance between 2 points is 0, then those are called the same points. The distance from x to y is equal to the distance from y to x, and the most important one here is the triangle. And now we need some water. The triangle inequality, basically stating that if you take a detour, you're going to pay a little bit in terms of distance. Sorry for that. So basically, the distance between x and z always is smaller than going from x first to y and then from y to z again. If you have this, as a distant metric, you can reduce the brute force costs of comparing everything versus everything. And how does that work? You can build a BK tree. There's a nice class publicly available as well on the internet. Basically how it works, it picks a random word or name out of the database as being the root node of the tree to build. So let's say book is here the root node. Now I'm first going to build this tree. So suppose hook comes in. Book and hook, the distance was obviously 1, right? Replacing the B with the H, so the distance is 1. I didn't have an edge yet with the distance of 1, so I'm building this, attaching this hook to book. Oh, I didn't think of that, but okay. Attach hook to book and give that a distance of 1. Now, second word that comes in, bool. Don't worry, I won't go through the whole tree, but it is important to get the concept here. So bool, difference in 2 letters from book, right? The last 2. I didn't have an edge 2 yet, so I attach bool with the distance of 2 to book. Last one, suppose cook comes in. I compare that to book first, I see a distance of 1, go down that edge, and then see hook, and then calculate the distance again of hook to hook. But what's important to realize is that all the elements on the left, say subtree of this tree, have a distance of 1 to the root node. And this, in combination with the triangle inequality, so suppose I've built this tree, this is my entire dictionary of the G database, and now Chris comes in. Chris has a distance of 5, right, to book, because I have to substitute 5 letters of Chris to reach book at some point. So 5 distance, which means I would need to create a new edge. But the nice part about this triangle inequality is that I only have to search now. Suppose I want to know all the words within this dictionary within a distance of 2 from Chris. Now, because of this triangle inequality, I have 2 cutoff points, because 5 minus 2 is too close to the root word, and I'm 5 away from book, and 5 plus 2, which is irrelevant in this case, but has a distance too far away from Chris already. So I can cut off by that trick the nodes 1 and 2. I don't have to search this whole space anymore. Hook, hook, book, ball, and bow. So that reduces the cost of the brute force by quite a bit. Of course, and it also makes intuitive sense. If I'm looking for Chris and distance of 1, all the words, I get a bigger cutoff, right? I have to search 5 minus 1 and 5 plus 1, so I can cut off more. All the 1 to 4 and 7 and above I can cut off. If I have a wider distance, I want to search, say, 4, I have to still look for 1 and 9 and above. So using this trick, you can cut down the costs of searching this brute force method by approximately 90% if you're using a distance of 1. At least those are our typical observations. So building that tree, that doesn't take too long. It's like 5 minutes for a 2.7 million dictionary. And typically all the words within a distance of 1 of a 12 million, 2.7 million dictionary would be done within a second. So that's pretty fast compared to calculating all the distances. Still, if you would be doing this within the 1 second, I still have only one comparison. So if I have a S list of like 5 million rows, it's still 5 million seconds, which will still take too long to calculate, even if you parallel distance. You can, however, use it, and that's not covered in this talk, but you can, however, use this to make more sophisticated comparisons for the matches that don't match from the next method. So the tokenized approach. I'm not sure whether, well, let me explain. The first thing is we break the name up into components. So ABN AMRO Bank would be 3 words. You can also make n-grams of it, like ABN, BNB, or no, BNA, like the first letter of AMRO, etc. You do this for all the names in both G and S, and you get 2 matrices. And to demonstrate, ABN AMRO would receive a token for the word ABN and for the word bank. Well, let's assume it's there. But RBS would definitely receive a token for RBS and bank. Rabobank NV would receive for Rabobank and NV. So D is the number of words in the dictionary. So you would have 2 matrices here. A number of elements in G times D for the ground truth. And the number of elements in S times D for S. So they've been tokenized using the same tokenization function. So if we multiply these 2, you get the inner product, of course, in R, the result matrix, which would have a score, a inner product for all the elements of G, right, the 12.7 million names, and here all the candidates in S being matched to that. And why we go through that lengthy discussion is because if you normalize the rows of G, so you give them a score and normalize them to have a distance of, or length of 1, I should say, and do the same for S, but then the trick is that multiplying these matrices results exactly in the cosine similarity of those two names. Well, that's expressed by this function, and automatically, because both vectors have length 1, the inner product also will be between 0 and 1. So by normalizing the token vector, we get the cosine similarity. Now, this allows us to do the same number of comparisons as we did before in the brute force method, but because this these inner product as a distance metric are very, very cheap to calculate using SciPy and NumPy. We'll show you a little bit on that later. And these are quite cheap to calculate, and we can even calculate on a GPU cluster on a GPU card. So let's take a look at some of the stuff you're going to run into if you're trying to make this tokenization work. Well, first you have to realize there's a pre-processing part and there's a calculation part. And the pre-processing part, I think important to realize there is that none of these are too time consuming to do for at least the scale of problems we're dealing with. So typically each of these steps can be done under 5 minutes as soon as you have them working, and there are some tips on there to get them working as in practice. So reading the data from Hive, I started out with this beeline command, redirecting it to the CSV file. It looks perfectly fine, and there's nothing syntactically wrong with it, but this runs out of memory. And we have a pretty decent cluster, I might add. So the tip there would be just work in UE, run your Hive script there, that's for sure not going to run out of memory, and then pull the file from HDFS, replace this, inside this file you pulled from HDFS, you replace the separator token with something more user-friendly than typically appears. And thanks to John for pointing this tip out, which took you about like half a day or so to make this work. So this saves you half a day, that's nice. So then tokenize McDonald's. Any idea what's going to happen here in practice? Sorry?
Code error.
Coding error, very good. Yeah. We've all seen this before, perhaps with the byte different, but this happens a lot. So cleaning is a really important thing to think through. We decided to replace dashes and underscores, I should say, with spaces. That's also an important thing, because else you get strange matches. Throw out the punctuation marks, and then you can still decide whether to go for ASCII or or Unicode, I should say. Or you could use Python. It's on video, so Gio knows that I said this. The G matrix. So we're going to tokenize this taxibedrijf M van Zeeman. And actually these are the tokens that come out. So that's if you use the standard implementation of scalar. And as you might notice, the M here is missing, which is quite a pain if you're starting to match names, which are already very short, and you don't want to miss out the individual letters. So make sure that you, in the standard token pattern, so the standard token pattern typically only considers tokens of 2 letters or more. So make sure to include a different regex, which allows you to capture single letters as well. You don't want to lose information on such a short document as a name. By the way, if you want to do n-gram matching, 3-gram, it's really, really easy in sklearn in the TF-IDF factorizer. You just have to enter that token pattern, and you have that running. This is just to show, like, the key point here is like taking you 2 minutes for a real size matrix to build this complete tokenization matrix. So this gives me the TF-IDF score for each name in the ground truth table. So, if you would match, so now we're going to, we've built this tokenizer for G. Now we're tokenizing a to-match string. And I did a little jump forward, so I matched Jonas de Man Nederland against Nederland Nederland, and it gives out a perfect match. What's happening here? Any idea?
Anagram.
Sorry?
Anagram, no?
No. No.
Yeah, but color on your
Jonas de Man does not occur in the other
That's it.
place, so it is ignored as...
So if you scroll down all the way in sklearn documentation, which is really nice, but honestly I don't read all of it before I start using the methods. It says somewhere that the standard TF-IDF transform function of sklearn ignores tokens that have not been seen before. Which is kind of unwanted, I think. If you get a 100% match on, then the business will look at you like, are you really sure that these two are the same?
I wanted to ask how the inner product works if it has tokens that do occur in S or G, but not in the other one.
Yeah, you can follow two strategies. Basically, either you build your own transformation function in which you add a few elements to the vector and then cut it off after normalization, and then do the inner product. So that's one way. The other way would be to extend the dictionary by building it on both G and S. So that's typically that's a practical.
To make the corpus.
Yeah, you first combine them to make the complete corpus, but then you would end up with 5 million words in your dictionary. Do note that sklearn provides you with all the functionality you need to build your own, how do you say that, custom transformation function. And then this is the formula you need if you're using CSC, sparse matrix format. It's basically using G.S.T. Sounds simple enough, right? And then all you need to do is multiply G with S.T. So here you have a row, a name with only one word. Here you have a name with 2 words, and the last one is with 3 words. You multiply that with the tokenization, the tokenized version of the name in S, and then you get this column vector. And what you need to do is find the argmax, and the max score gives you the best match. So in this case, this name, which is tokenized, matches best to the first entry of G. Now let's take a look, and it's also a little bit test of the eye, so I'm not sure whether this is going to work in the back of the room. We're going to look at 0.01% of the matrix G. And I've, because Alex studied astronomy, so it's like a nice guy. What do you notice? The white dots, by the way, are not stars, but are of course non-zero values in the TF-IDF matrix. Anyone? Yeah. Oh, that's great. Yeah. You have this column here. Any idea what's happening there? Yeah. Like a PV is a very common extension in the Netherlands for a company. Occurs a lot of times. And if you, it might be important because if we have a company as a PV in the Netherlands and a limited in London, you do want to have a way to separate them out nicely. So it's common to throw away stop words, but not again if you're name matching, because then you have very little information per name. So it's not a big document which you can throw out a lot of. At least we consider that to be too expensive. It does have a drawback, of course, including these stop words, because the density of the resulting matrix, so G times S.T, will be much higher as a result of this than the original input matrix. What that pragmatically means is you'll run out of memory for sure if you're going to multiply the complete G with the complete S matrix, right? Because this is what G looks like. So there's a lot of entries here, a lot of non-zeros. If S has a similar structure, it will have a lot of white dots all over the place. So it's 4,000 times as dense, in our case, as the original input matrix says. And the original input matrices are roughly the size of 2 gigabytes. You easily run into 10, maybe more, terabytes for the product. So it's not as easy as I first showed you. So then we have 3 contestants for the calculation part. We have what we call Cruncher. It's actually called that. It has 48 cores and a half of gigabyte of RAM. A Tesla, which has 3 GPUs in it. 3 times 12 gigabytes. And we have a Spark cluster with 150 cores. I wanted to do a vote, but nothing fancy. Who thinks the Cruncher will win? Well, limited enthusiasm there. Who thinks GPU will win? Cool. So the rest, I presume, votes for Spark. Okay. NumPy, actually SciPy matrix multiplication, these are very sparse. It's like with the pizza, right Jonas, the 5th slice and onwards are going to actually cost you more, but the first 5 slices are really cheap, really going easy. And that's actually the same message here. So if you multiply G with S.T, and S.T only has one slice of the matrix, so one row slice, that costs in terms of computation time about as much as doing 20 of them. So 20 is maybe a fraction more expensive. Even 100, it's not even twice as expensive as doing a matrix multiplication with 20. So that's an important observation. So you want to do a nice slice, but not too many, because after like 100 or so, the costs go up almost linearly. If we look at the line profiler of the code, then we see that actual matrix multiplication takes about 80% of the time, and the extraction of the argmax and the actual score takes about 20%. So we presume that this code is close to optimal. How fast can we go then? We can go up to 140 matches per second by using this method on a single CPU. Well, that's pretty neat, I would say, but you're quite underwhelmed. Okay, so Tesla GPU multiplication. We've tried sparse, the binding from Anaconda. We've tried TensorFlow to make that work. Problem is that sparse matrix multiplication in a distributed way on GPUs is turning out to be incredibly difficult. There are a lot of papers on it, it appears, and the codes, I would say, are not so very accessible, and I'm putting it in a very polite way. So what Alex actually did, he built this custom kernel, but it's really difficult to parallelize these sparse matrices, because you don't know at which point to look in memory to do the multiplication. You have to find the index, and you cannot guess where the non-zero elements are exactly. So what we did is a sparse matrix times a dense vector. So this S vector had to be dense, so the zero is still in there, and then the sparse matrix would be serving as a, how do you say that, the vector that determines where we look for values in memory. We didn't distribute the data across the GPUs yet, and so we're using a single GPU at the moment. Sorry, and we didn't push all the full matrices onto the memory of the card up front, and then only making the calculation in slices. So although further optimization are possible, we've been managing to get to 50 matches per second on the GPU at this moment. So if anybody here has a sparse matrix times sparse matrix multiplication package lying around, please approach us after this talk. We'd love to. What is important to note is that this sparse times dense multiplication was a lot faster than doing it on the CPU. I'm saying it right, huh? Now, the Spark cluster, we tried, there's standard TF-IDF in Spark MLlib that uses hashing and that uses sparse vector representations to multiply in a distributed way. And that's kind of slow. And also the hashing creates unwanted effects of matching, again, companies for which the hash value is exactly the same. And that, again, doesn't resonate nicely with the business. So what we did, we created broadcast variables of these tokenized matrices, like 2 gigabytes per piece. And we pushed them first to the workers. And then these workers, all they got was a range of rows to work on. So they got the command from, I want the result from you, from slices, rows 0 to 9, 10 to 19, etc. So we made a very lightweight RDD. And then what the workers had to return is, as just as being a kind of a standalone CPU, is the result of this G times S.T for these specific slices, the argmax thereof, and the max score. So we would get, after a collect, a nice list of, for row 1, or sorry, for row 0, this is the best match with this score. What really was nice is that this would require substantial addition to my code. No, just kidding. It was 1 row extra to, well, just a couple of lines extra code to make this work on Spark. Whereas for PyCuda, you needed to really dive into C++, so it was really nice that you could do the pre-processing in Python and then call that, but still the stuff you had to do is quite extensive. Whereas this was like half a few hours of work to figure it out exactly, but all you need to do is add dot value, and in which case the broadcaster's variable is available to you. And then you could simply call this mapper on this RDD. So this was the amount of extra code required to make it run on Spark. By doing this, we were able to reach 2,000 matches per second, which allows us to do processing instead of, well, the brute force you recall 19,000 years. We can do that now in close to 5 minutes. So to summarize, the prices are, well, at the moment, unless somebody approaches us with an awesome sparse matrix multiplication engine, GPU finishes third for this job, beaten by the CPU, but definitely the first prize goes to Spark. Thank you. Any questions or suggestions?
You mentioned there was an issue that some of the tokens occur in a lot of namespaces. Did you consider some kind of normalization to weigh tokens differently if they occur in a lot?
Definitely. That's what we did with TF-IDF. So the IDF score, the inverse document frequency, would typically lower the relevance of the tokens that occurred in a lot of names.
Was it over documents? I thought it was inside of the document. The name had
so the term frequency is typically 1 in this case, right? There's not that many companies that have a double name, or two times the same word inside one name. The document frequencies need very relevant.
so it was over documents.
We definitely did that. Yeah. So that's that would definitely be a a mistake not to do so. So yeah.
Okay.
Yeah, thanks.
Did you have any way to know whether your matches were good at all, except for inspecting them manually?
We did a histogram of the scores,
Yeah.
and we bucketed them like